Welcome to the GAIN Innovative Materials Research webinar. I'm Holly Powell, Operations Manager for GAIN. The purpose of today's webinar is to introduce a potential new DOE program on advanced and innovative materials research for fuel cladding for advanced reactors. This webinar will provide the opportunity to inform programmatic objectives and gather feedback from various stakeholders in the following areas: innovative cladding materials research, characterization and testing methods, new methods for qualifying materials quicker, as well as informing research needs spanning the next 20 years. The agenda is divided into 3 segments. First, we'll have introductory presentations, followed by presentations on advanced nuclear industry gaps and needs. The final segment will be a focused discussion on those gaps and needs. And this is where we want to hear from you. We want to hear your thoughts, any questions that you might have, and the feedback that you're willing to share. But please don't feel that you need to wait till this focused discussion to share feedback. If a thought crosses your mind, put it in the chat and we'll address it as we are able. A few things, housekeeping items. The webinar is being recorded. Your attendance is consent to be recorded. Please keep your camera off and your audio muted. Disconnect from your virtual private network in order to avoid technical difficulties. The presentations and the recording for this webinar will be posted on the GAIN website within a week or 2 after today's webinar. And please use the chat or raise your hand so that we can gather the critical feedback that we need to inform this program. We have planned for about 5 minutes-ish of question and answers after each presentation. If we don't get to your questions during that time frame, we'll circle back during the focus discussions. And with that, I'm going to go ahead and turn the time over to Sue Lesica from DOE.
Thank you, Holly. Are my slides in presenter mode?
Yes.
Okay, great. So as Holly said, I'm Sue Lesica from the Office of Nuclear Energy at the U.S. Department of Energy. And first, I wanted to start off thanking you all for joining us today. It's very important to us to get as much input as possible. And so we're looking forward to having this be a very interactive meeting today. So as Holly mentioned, we are looking forward to hopefully have a new program for FY23. Just to give you some background on how we got to where we are today, the department does reviews for long-term planning of our programs and therefore our budgets. And in that process, looking at what our programs were and what we need in order to continue the success of nuclear energy in the US and in the world, we identified one area that has recently had a gap in development, and that is longer-term development of fuel cladding and in-core materials. We group those two together, cladding and in-core materials, because often they are the same materials or similar materials because they see similar environments, high radiation, high temperature, etc. And so as part of this process, in the FY23 presidential budget request, we did include a line item to begin a new program focusing on these types of materials. So far, the House has given us marks for what they would like to fund in FY23. We're still waiting for our marks from the Senate, so we don't know yet whether or not this new program will be funded. But if it is, we wanted to gather input and develop the program as much as possible this year so that when the funding does arrive, we can hit the ground running and start getting research and research results as quickly as possible. And so that's why we're here today, so that we can gather input to put towards the development of our program and develop a priority list so that things can begin as quickly as possible, should we receive funding from Congress. So being the sponsor here, I thought, as required, we should start with a budget slide. And so here is a breakdown of the fuel cycle of research and development budget from 2021 through the budget request. And there are several different research areas under fuel cycle, but one of them is the fuel cycle core research and development, and that's where this program would reside. And the fuel cycle core research and development has many different aspects, but as part of our 2023 request, we included approximately $8 million for this new program. So here's a list of the different areas that the fuel cycle core R&D plans to support. And the new innovative nuclear materials programs, as listed here, our goal is to continue our leadership in nuclear materials and our competencies in research and development for nuclear materials to support nuclear energy in the US. We also want to continue to build on and capitalize on the developments in modeling and simulation capabilities, on instrumentation, on testing, characterization tools. All of these put together should have the result of making the process of going from materials discovery through research and development to commercialization be much more efficient and quicker process than it has been in the past. So here we go. So here's the goal of the workshop. We want to seek stakeholders' input, and in our case, stakeholders is defined as the people that will actually use the results of the research, as well as the folks that will be doing the research. So this includes the reactor designers and suppliers, to the researchers at universities, national labs, EPRI, etc. And so with that, we wanted to get input into the development of the program, both on the focus of the program and how we plan to administer the program. We also have a list of what we're not looking for. We are very much focused on research and development. That is the area that has been identified as the gap. We have a lot of other work going on in the demonstration and further down on the commercialization line. So we're staying more, our focus is much more on the lower TRL type of research. So next we have a list of questions, really just kind of to spur some thinking of what could be needed, what type of materials do we need, what type of models do we need in order to predict how the materials will perform and how the environment will affect mechanical behavior further down the line. As you know, these reactors last for a very long time, and we need to be able to predict long-term behavior. I won't read through this whole list in detail, but I did want to put it up just to kind of get you started thinking in this direction. I also did want to talk a little bit about the administration of the project. We've also been asked, how will we fund the research? Will it be direct funding? Will we have competitions? That type of thing? Will it be cost sharing? And traditionally, we don't do very much for cost sharing for this level of R&D. So we would, our plan right now would be funding the work directly, or either directly or through competition. And really, that portion of the program has not been defined yet. Once we identify what our priorities are, we will then look to see what is the most efficient way in order to fund doing the work in those different areas. So if there are areas that are much more suited towards, say, a national lab, that is an area that we could do direct funding. If it's an area that's more suited towards university or industry, then a competition would be in order, and we would look at funding research in those areas in that way. So the administration still hasn't been decided, and once we have more information on what we're going to actually perform the research on, I think that will really help us define how we administer the program. So that is the end of the slides that I have. I would be happy to take any questions. There is the chat feature. If you prefer to write your question or comment in there. Okay, it doesn't look like we have anything in the chat. Okay, I think we can go on to our next presentation then. So in order to pull all of this information together and inform our decision-making when it comes to the priorities of the program, we have Stu Malloy from PNNL has graciously volunteered to do that with us, and his experience in this field is going to be extremely valuable to us in developing that. And so now I will pass it on to Stu. Thanks, Stu.
Okay. Thank you, Sue. And I hope you can see my first slide. It
looks good.
Okay. Yeah. So as Sue said, that I'm going to dive sort of a little bit deeper into this specific research area that we're really trying to hopefully get started in the next year. My name's Stu Malloy, and I'm a nuclear materials advisor at Pacific Northwest National Lab, which I've only been in that position for about 3 months now. Actually, previously, as most of you know, I was at Los Alamos, and I was there for about 33 years. So I have a lot of experience in developing and testing materials for cladding applications in reactors. So what I wanted to start with, which I think everybody knows, is that materials, as much as we'd like them not to do this, they can actually fail in nuclear systems. And that's what, in developing materials in this program, we'd like to avoid. One failure that happened many years ago was, as shown here, where an actual duct that saw significant swelling failed when they went to actually pull it out of the reactor and leaving the fuel in there. So that's not something you'd want. Another is grid to rod fretting, which can happen, for example, even in just light water reactors, where you can go right through the cladding with sort of normal operations. Crud is something you want to avoid as well, where it's just sort of corrosion deposit that can collect in your reactor, and then also larger scale corrosion, as shown in this Davis-Bessey reactor vessel head degradation is something you want to avoid as well. So we want to be able to develop materials that last longer in reactor, that we also know the lifetime very well, so that we can avoid having a failure before we actually take these materials out and replace them. So in order to develop these new materials, we have to know what the extreme environments are. So the extreme environments for a cladding material come from different things that they're in contact with under irradiation. So for a high dose, developing a high dose radiation tolerant advanced reactor cladding material, you have to deal with many different areas. First, you have to deal with interaction with the fuel, especially in a metallic fuel. If the cladding or the fuel is going to stay in this case, we want to push it to higher burn up. If it's going to stay in the reactor for a long period of time, you can eventually get interaction between the fuel and in a metallic fuel that can be pretty large, between the fuel and the cladding. And as that continues to react, it can reduce your cladding thickness, which reduces the effectiveness of your cladding to hold the fuel in the reactor. So there we'd want to be able to develop either better alloys that actually resist that without having to add a coating or a liner, or maybe something where we're actually adding a coating or a liner to the fuel. And just a reminder, please put your phone or computer on mute if you're hooked in right now. Also, if you want to push them to very high burn up, then, for example, if you're pushing to 10% burn up in the fuel, you're typically around 100 dPa in the cladding. So as we push to higher burn up levels, the radiation damage in the cladding goes up significantly as well. And we know, and I'll go into this more in the slides after this, we know HT9 or other ferritic martensitic steels do have good radiation tolerance as a cladding material, but they do have some limitations as well. And so we'd like to, in this program, develop better, more either advanced ferritic martensitic steels or oxide dispersion strengthened steels or advanced alloys. And we'll talk about that more as we go through the workshop. And that hopefully is going to push us to higher doses. Can we get out to 200, 300 or more dPa? And also, can we withstand higher irradiation temperatures? Some of the advanced reactor concepts, especially, for example, molten salt reactor, want to actually push to higher irradiation temperatures, and there we may definitely need to develop better materials. Yeah, somebody needs to mute their phone, please. And then especially with different reactor in the advanced reactor types like lead fast reactor or the molten salt reactor, you need to worry about interaction between the coolant and the cladding. And so there you either may have to add different alloying elements to make a material more corrosion resistant, like aluminum or things like that. And so that would have to be looked at as well as you're developing material for this type of advanced reactor, whether it's developing against corrosion for lead reactor or developing against corrosion for a molten salt reactor, where the alloying elements you may add might be quite different for each of these reactor types. So you've got some very extreme environments, and some classes of materials may work better for one environment and others may work better for other environments. So as we'll get into more near the end of the workshop, there's a few different classes of materials we'll be looking at for different advanced reactor types. So one example, though, which I want to use to show you what limitations we have in even a very good material that is quite radiation tolerant, is HT9. So HT9 has a lot of the features that you'd like to have in a cladding material for good radiation tolerance. It has this tempered martensitic lath structure, as you can see here on the right. And those laths provide sites for recombination of interstitials and vacancies that are made under radiation that help to be able to push this material to higher doses. It also has fine carbides in the microstructure and other things that give it good void swelling resistance. And this is not anything new, probably not new to anybody in the audience as well, that it does show excellent void swelling resistance. And even back in the 80s, as you see on this graph to the right, HT9, which is shown as this lower line below, showed good, even in 1982 when they were testing it against other austenitic steels, showed good void swelling resistance out to about 80 dPa, and they've now since even tested it out to almost 200 dPa in TEM samples. So it does show good void swelling resistance, but in one of the studies, and others have shown this as well, you can see that there are some limitations also to HT9, and one is that it hardens significantly at lower temperatures. You can see this in a component that was tested after radiation in the fast flux test facility called the ACO3 duct. And there you can see a few things that are quite evident. One is that as you lower the irradiation temperature, so this is 416 here, 398 and 381, as you lower the irradiation temperature, you get significantly more hardening in the material. And going along with that, you also get a reduction in the uniform elongation in this material as well. And if you put all the data together, you can sort of see that here in this plot of 0.2% offset yield stress versus irradiation temperature. At the higher irradiation temperature, above 420-ish C, there really isn't much change in yield stress at all. But as you decrease the temperature to 400 C and below, you get significant hardening in this material, which leads to a reduction in the fracture toughness, which is shown here. These green dots here are samples radiated at 377 to 398 degrees C. This is work that T.S. Biyun did many years ago. And he also measured the ducted to brittle transition temperature, and you can see that along with the hardening, of course, leads to a increase in the ducted to brittle transition temperature. And the sodium handling temperature for a sodium fast reactor is around 200 degrees C. So you're getting to the point where you're close to becoming brittle at the sodium handling temperatures, which is not what you want. So one issue is low temperature embrittlement, and it's strongly connected, of course, to its microstructure, which is shown here, that you can see a fine distribution of interstitial and vacancy clusters, but also G phase and alpha prime precipitates at the lower temperature. Whereas at higher temperatures, you get some loops, but they're not nearly as high in density and they're larger in size. So they don't really lead to significant hardening in the material. You do see a little bit of void swelling in this material, but that's quite low, only 0.3% after 155 dPa. And then at higher temperatures, there actually wasn't much of a change at all. So the microstructure is clearly important, and that's going to be important when we're developing better materials for these cladding, advanced reactor cladding applications. So, what are the limitations in service life with HT9? The first one, of course, was what I pointed out clearly here is that low temperature embrittlement below 400 degrees C. There are some better ferritic martensitic steels that don't show as much low temperature embrittlement, but still even below 350, these materials do show some low temperature embrittlement. Fuel clad chemical interaction. I didn't go into this, but it does show that for high dose irradiations or high burnup irradiations and with HT9, you do start to get interaction between a metallic fuel and the cladding. So that's something we would have to either put in a coating or a new material to avoid. And then one of the big issues is low creep strength. So actually, even though HT9 is a really nice material, but up above 600 degrees C, it does show reduced creep strength even over an austenitic stainless steel like 316L stainless steel. So can we develop, especially if we're trying to have materials for some of the advanced reactors like the molten salt reactors, where they want to go out to maybe 700 or even 800 degrees C, we really would need to improve the creep strength to use a material like this for that application. And then you also can run into radiation-induced segregation at high doses, and also some second phase precipitation. And then I don't even really get in, didn't show any of this here, but clearly there are severe corrosion limitations if you're trying to use HT9 or lead, or HT9 in contact with coolants like lead or molten salt. So these are some of the limitations of one of the best materials that is out there. And so these are the things we'd like to try and overcome with new and improved materials. So what's the overall vision of this program that we have, or at least right now? We might modify it based on our discussions today, but our overall vision is to develop and test innovative new cladding materials with the potential to revolutionize and transform future nuclear energy applications, especially these new advanced reactor that are being developed right now. So that's developing new alloy compositions, whether it's high entropy alloys or some other alloy. It's something new that may be able to meet the corrosion issues and the high dose radiation limitations that we have for some of these applications. Coatings to eliminate fuel-clad chemical interaction, or a better material that has improved corrosion resistance. Innovative microstructure. So if we, as you saw, it's the microstructure that really leads to the reduction, the extreme hardening and the reduction in properties in these materials. If we can come out with, through different manufacturing techniques, new innovative microstructures, maybe we can avoid the significant hardening, for example, at low temperature. Innovative manufacturing and joining methods. So in a lot of these new materials, joining is not as simple as for a ferritic martensitic steel. So along with developing a better material, you may also need to develop the joining method that goes along with that material. And I'll show this even more in some of my slides coming up, but we need testing methods to investigate high dose radiation tolerance. We would love to have a fast test reactor in the US, but we haven't had that since FFTF. So hopefully maybe VTR goes forward and we can actually have a place to do higher dose radiations. The highest dose rate we can get right now is through HIFER irradiation. So we need a place to do high dose radiations, and one of the ways to do that is, as many of people know, is we can get high dose radiations with ions, but we need to make sure we've correlated that well with neutron radiation as well. And if we're doing a very small volume ion radiation, we may need to develop better mechanical testing techniques to test over that small volume to get that sort of data out of those small irradiation areas. And we'd like to develop methods to better or accelerate material qualification for cladding. And you'll see in some of the next slides that that's also a aim for structural materials as well. So where does I think many of there is a bit of there are other materials research programs in the Office of Nuclear Energy, and what I'm aiming to show here is how they do complement and work with each other. So some of these actually are not fully funded yet, but these are what we are proposing. These are proposed programs that would be proposed in FY23, and some of them are already here. So of course, there's the innovative materials for advanced reactor cladding that we're talking about today. That's centered on cladding for advanced reactors, and it's centered at the lower TRL level. So you can see it's pretty much from TRL 1 out to TRL about 4. And then as you move out to higher TRL levels, there is a new program that was funded a little bit in FY22, and we're hoping to increase the funding in FY23, and that's called the Leading Innovation in Fuel Technology, or the LIFT program. And it's a metallic fuel qualification program where they're actually doing planning to do more testing and research on HT9. But if what I can see as a connection is if we can develop better materials in the IMARC program, it may be when we get it up to higher TRL levels, we could pass that into the LIFT program. So a nice coordination there. And then for the light water reactors, there's the accident tolerant fuels program that's been going on in the Advanced Fuels campaign, and that develops better cladding and fuels for light water reactors in the case of a possible loss of coolant type accident. And then on the NE5 side, there are also some large materials programs. One of the largest ones just started this fiscal year is Advanced Materials and Manufacturing Technology, and that can deal with lower TRL all the way out to even deploying. So that in that program, they're really interested in advancing the qualification or increasing the qualification rate significantly. But that program also has a strong correlation with the other two programs that have materials work in them as well. The Light Water Reactor Sustainability Program, where we're really pushing reactors to longer lifetimes. And then Advanced Reactor Technologies, where they're looking at the different advanced reactor, the structural materials and different advanced reactor technologies, as well as the other important aspects of pushing those advanced reactor technologies forward in the future. And so if you look at both of those, all of those materials research areas, the ones that have the most materials work in them is the Innovative Materials, which is mainly just a materials program, Innovative Materials for Advanced Reactor Cladding, and the Advanced Materials and Manufacturing Technologies. And so those, I don't know why it's not showing up here, but so everyone, this shows up and sometimes it doesn't, but anyhow, I guess you can't see this, but this is Advanced Materials Development and Innovative Cladding Development. So all I'm really trying to point out here is that there probably will be some materials that being developed in the Advanced Materials and Manufacturing Technology program that also have strong application to cladding. So I can see a strong connection between that program and the IMARC program. And on the other hand, as well, there may be some cladding materials that developed with a really good, excellent radiation tolerance that may have strong connection to structural material application too. So these two programs I could see as strongly complementary to each other as they move forward. But the other that I didn't put on this list but is really important to all these programs is nuclear energy advanced modeling and simulation. That, as already pointed out by Sue, that developing models for understanding the high dose radiation tolerance in these materials is really important, is something that we would lean on with the NEAMS program in our Innovative Materials for Advanced Reactor Cladding. But that NEAMS program also develops models that would help understand cladding development for the LIFT program or the accident tolerant fuels program, as well as advanced materials and manufacturing technologies, LWRS and ART. So that this program, Advanced Modeling and Simulation, has a strong connection to all of those these materials programs. So what innovations, and this probably is not a full list, but what innovations are going to be required so we can develop this advanced reactor cladding? First of all, if we're going to develop some better advanced alloys, and some of the alloy classes like high entropy alloys or others, there's a huge number of different alloys that you could possibly look at. So we really need to look over a large. Yeah, somebody. Okay, I guess they muted. We need to look over a wide range of composition space. So that will be important in narrowing down the compositions to one that may specifically apply to cladding that could actually have an application in an advanced reactor in the future, or developing better. I mean, when we talk about cladding for these reactors, in some cases the cladding is out to 9 feet in length, and it's a 0.5 millimeter wall thickness and 7 to 10 maybe millimeters in diameter. So that technology itself is difficult. So if we develop a better material, we need to be able to develop how we're going to extrude it or pilger it to lengths, the long lengths that are needed for these advanced reactor technologies. And if we're going to put in a coating to prevent fuel-clad chemical interaction, it's not just coating a little small section of tube. We've got to coat that whole tube on, and sometimes on the inside of that tube as well. So innovative methods of doing that coating technique are critical also. And then we need to hermetically seal this cladding when we put the fuel in it. And we know the methods for doing that for zircaloy or even HT9, but some of these new materials, we may have to develop new joining technologies just to be able to join these materials to make them hermetically sealed for high dose irradiation applications. And then, as I pointed out already, we don't have a test reactor in the US, for example, for doing high dose irradiations. And so we need high dose radiation testing techniques. One of them could be ion radiation on materials, so that we can really do one-to-one comparison of these new materials and do small scale testing on them to understand and how the changes in mechanical properties, or what the changes in mechanical properties are after high dose radiation in those materials. So I did want to point out how can we obtain some of this high dose radiation data. I think, just to make sure you understand, I mean, even if we had a test reactor, at most, if you just take Bore 60, for example, a sodium cooled fast reactor, at most you can get is about 20 dPa per year type total radiation dose. So if you want to understand cladding changes in cladding from neutron irradiation, that in itself could take 5 years just to get that irradiation data. So in many cases, we're going to be relying on previous data. And there is, from the Nuclear Systems Materials Handbook, there's data out to 100 dPa on mostly austenitic stainless steels, maybe a little bit on ferritic martensitic, but mostly on austenitic stainless steels. From this recent, from about an analysis done about 10 years ago, which I just summarized in this talk, on the ACO3 duct, we got some data out to about 155 dPa, but over a specific temperature range. From materials that were irradiated in FFTF, there were actually some that went out to even 200 dPa. So there is a lot of irradiation data available. What we're trying to do with an irradiation and a collaboration with TerraPower is actually, this is also this is also an irradiation that was done in the Phoenix reactor. There we went out to about 75 dPa, and each one of these irradiation campaigns can take 5 to 7 years in itself, right there, just for the irradiation. And unfortunately, with this matrix irradiation, we've been waiting now almost 10 years just to get the samples back from France. So one of the things we're trying to do is take advantage of the fact that we did irradiate material to a high dose and irradiate it further. And so through a collaboration with TerraPower, we sent some of the ACO3 duct material and some of the FFTF MODA specimens to Bore 60, and they were irradiated in their reactor till about 2019. And we're now working with TerraPower to hopefully get those back in the next year or so. We'll hopefully in early next year, we'll have those specimens. So that will be very important data, because that'll get us out to even up to perhaps up to 250 dPa. But to get, I mean, that's not even on these advanced materials that we'd like to develop here. So how are we going to get there? You know, I think one of the areas we're going to have to lean on a lot is high dose ion radiations, but we'll have to couple that with strong modeling and simulation so we can understand that data and correlate it with the neutron radiation conditions that we'd like to use those materials at. So it's a challenging problem. It can take a lot of time. And so we're going to have to use all of our resources to get this high dose radiation data on these materials. So the overall aim of this workshop, which we've already said a couple of times here, is to get input from you, get input from industry, get input from national labs and universities, so that we can lead to developing the priority research directions for this new program. So what we're going to have after this, I mean, we have a little bit of time for questions, but after this, we do have some additional talks from industry, a little bit of summary of the workshop that was held at the ANS meeting, which I know many of you couldn't attend. So I wanted to make sure I summarize that for you. And then they'll be open to you. I'll lead into each area, but for getting input from you on different subject areas for this program. So with that, I think we do have a little bit of time for questions.
Stu, there
Yeah.
was a question that says,
Okay.
can you tell what materials need to be joined in the reactor core? Is it functional or structural joining, or both?
So yeah, the materials that we need to do joining on are these materials for cladding. So yeah, Brian, okay, there you go. So yeah, the materials that we need to join are those for cladding. So they, in order to have a functional cladding material for an advanced reactor or a new fuel, you need to be able to seal that cladding at the end. So whether it's a friction stir weld or a regular TIG weld or something, it has to be one that can give you a hermetic seal of that cladding material. So, I mean, of that cladding to hold the fuel in it. So, and then I see one that says, can we get the slides? And of course, yes, we are going to post these slides afterwards. Teresa already answered that. Let's see, the presentations. Okay. So any other questions? It looks like I covered one, but any other, you can either put them in the chat or you can open your microphone and speak as well. So
I have a question, Stu. This is Osman Anderoğlu from UNM.
Mm-hmm.
So most material calls are for very high dose irradiations or very high temperatures for instance, molten salt reactors. There hasn't been any specific calls for heavy liquid metal coolants, the reactors that use heavy liquid metals as coolants. Would there be any, I mean, is this a, there is a lot of research in the Europe, but in the US, I don't remember any recent calls. Would there be any calls for LFR materials development?
Yeah, so I guess going back to a little bit on what Sue was saying, exactly how we will set up the funding in this IMARC area is not decided yet. So will it be a competitive call, or will it be work packages at different national labs, or some combination of both? That's to be decided after we determine the priority research directions and see what sort of funding hopefully gets approved. So Will there be a call? Well, I mean, that is one of the areas that is important to industry. You know, we saw a talk at the ANS meeting from Westinghouse, which is really interested in the lead fast reactor. And so that is one of the areas that we want to develop better cladding, improved cladding for. So if we do it through a competitive call, then there may be a call for that in the future, but that's to be seen. So I don't know if you want to add anything to that, Sue, but.
No, that's exactly right. How we fund is still up in the air, but if that's comes out to be one of the top priorities levels, it certainly seems like an area that would be ripe for competition because there is expertise across a wide range. So competition would be a good idea for that type of topic.
Okay, so I see a few people with hands up. Mike Ickes.
Hey, Stu. Thanks for your presentation there. I appreciate you going over some of the stuff that was at the last meeting. Sorry, I couldn't join you in California there. I really just wanted to, maybe pile on to what you were saying. We have, I think, some good candidate material selections. We're developing the capabilities to test those in liquid lead at a lot of different conditions, that'll be necessary for us. And then, we're also developing the coating techniques that are going to be necessary for our materials, to protect against that corrosion. But, as you kind of hit the nail on the head with the big gap being access to fast neutron sources. I want to know, what I really want to know is this fuel cladding concept that involves a coating that we have going to stand up under lead plus neutrons, for high burnups, or is something like differential void swelling going to cause that all to fall off, or some other nasty thing. And that's just something, I don't think we'll get with ions. I haven't seen good correlation between void swelling that's been developed through ion irradiations versus neutrons. So, I really just wanted to, emphasize the importance of that to Westinghouse.
Thank you, Mike. And I agree. I would definitely want to see a neutron source in the future. But that does relate a little bit to one of the questions that Raj Iyengar I see has on put in the chat, and that is, can you talk a bit more about the viability of ion beam irradiation to get insights on neutron irradiation? There's been a very substantial program led by Gary Waz almost 6 years now that has actually done ion irradiations and done direct comparison between the ion irradiation and same samples irradiated in bore 60 to same doses at radiation temperatures, where they do an irradiation temperature shift to do the comparison. And they're getting some very nice correlation along with developing models as well, but they're getting some very nice correlation between the microstructures that you get at with a temperature shift in a, for example, grade 91 material or in a 800H material, and the same microstructures they got from irradiation in bore 60. So we're making some progress on that. Is it perfect? No, but I think that there has been some really good progress in those areas, and hopefully we can see more, maybe if some of that's in this program in the future. So.
Okay, thank you.
Yeah. Let me see, try and catch some of the other, Ken Ross.
Yeah, so I guess first of all, I'm really excited to see that this topic is gaining interest and whatnot. And I guess one concern I have is, over the past 7 years, I've been nearly consistently putting in proposals for technologies that could potentially solve some of these problems. And after, even with letters of recommendation from the owners group and major players, and after doing a lot of digging and really, arm twisting and stuff, coming to understand that there's, political or preferential, things on which types of groups people want to fund, And so it seems like the only way I can get some of these technologies to move forward is to go the SBIR route, which is frankly exhausting because I have to basically donate a ridiculous amount of my own time to help some of these technologies, be successfully done by other people. And so as you guys are formulating this program, I guess I just want to express a concern is, can we kind of look at what are the types of organizations that have the tools available to help move these things forward? And can we do it in a way where the people that have the answers don't have to hand off the technology to people that aren't necessarily the experts in that space, because that's how the funding has been allocated, or that's how the preferences are for that program as far as what type of flavors of money or who they're funding. So I just wanted to bring up that concern and wondering if there's a plan for this program to make sure that we can get the best technology on the table and minimize roadblocks relative to things that aren't necessarily technical.
So that's a good point to make. I guess one of the reasons why we're having these workshops right now is to try and start this program out with getting input from industry and national labs, but specifically the new industries that are looking at advanced reactor concepts, and see where their needs are. So if we can in this program address those needs in those advanced reactor concepts, then I think hopefully without any political concerns, we can get new information, develop new materials to help push those concepts forward. So my hope is that this will help, that this program will help that. And maybe Sue, do you want to add to that? Or
Yeah, I just wanted to add that, right now, at least for this program, we don't have any restraints. There isn't a focus on, say, universities or only focusing on industry or only focusing on national labs. So right now we do have the flexibility to put the money where it will be the most efficient and the most worthwhile to quickly get the work done. So right now we have that flexibility, and hopefully that will continue.
That's fantastic to hear. Thank you.
And I see Javier, you have your hand up.
Yeah, hi Stu. I have a
Hi.
quick one. I may have missed this, but I was wondering about the timeline for IMARC. When do we envision to start, and the whole duration of the program?
Maybe I'll let Sue answer that.
So it really depends on the federal budget process. If as we have many years in the past, we have a continuing resolution, then the program, this would be considered a new start. So the program cannot begin under the continuing resolution. We would have to have a budget passed in order for us to begin. So if Congress does decide to fund the program, once we have a final budget for the year, then we can begin. But we can't do it. We can't begin under a continuing resolution.
And do we have a vision of duration, Sue?
As long as there's a need to continue the program and a desire by Congress to fund it.
Okay.
So we don't see this as being just a 1 or 2 year project. We see a much longer term need than that. And particularly since we're focusing on the lower TRL, it will take longer for us to develop.
Exactly. Okay. Thank you.
Thank you, Javier. Let's see, I'm looking at the chat. I don't see anything, any other questions. I did successfully stop sharing my screen, so I did that.
There is one that just came up.
Arun, I see. Arun, did you want to just, so that I don't have to spend the time reading it, do you want to just open your mic or?
Yeah, hi Stu. First of
Hi.
all, thanks a lot again for giving the nice presentation that you also gave at the NS meeting. My question is, could you comment on dose mapping of certain candidate materials using both neutrons and ions? And I'm saying this because reaching ultra-high doses is indeed an ambition in future reactor concepts. But many of the key radiation damage degradation phenomena are more prevalent in the low, or I would arguably say intermediate doses, such as hardening, embrittlement, and ferritic steels, and also oxide dispersion strengthened steels, which continue to harden up to 400, 500 degrees C. So all doses will be needed. And I want to believe that certainly medium to relatively high dose archive testing of neutron irradiated materials that is available in the US is important to understand phenomena, and then have separate effect studies with ion irradiations. What is your thought on that?
So I think your question is centered around, I mean, have there been good dose mapping correlations between ions and neutrons over a range of doses? Is that sort of what you're saying, or?
Yeah, I'm saying that, but I also want to sort of, how can I say this? I'm also trying to say sort of as a caution that we shouldn't just be targeting ultra high doses and just doing that. We should not forget that a lot of key phenomena occurs or saturates by intermediate doses. So dose mapping is important. Whether we do neutrons or ions is a separate story. People argue this is better or that is better, but I think both are needed. We may not just do everything by ions, and we may not be able to do everything by neutrons either. So both have to go in parallel.
Yeah, no, I don't have much to argue with you about that. I mean, yes, I mean, if we, for example, for some of the materials like HT9 or other ferritic martensitic steels, they, their hardening saturates at low temperature after only about 5 to 10 dPa, 350 C. So maybe some of that work could be addressed through neutron irradiations, because we might have time to actually get some new materials into reactor and out to analyze a lower dose radiation response. But also higher dose, we'd like to do it with neutrons, but where we can correlate it and do it with ions, we would want to do that. And Gary, he put some nice comments in the chat, and there's actually a new paper out that had a nice summary of some of the research that's come out of this ion radiation program. But there is good correlation and good model development that's come out of that program, and if we can use that together, perhaps we can get good high dose radiation data on these materials without having to wait 7 to 10 or more years for doing it in reactor. So I agree, we need to do a combination of both. Completely agree that, and I think we'll use our capabilities where we have them to get that data. So, and I think Isabella, I think we have a couple minutes. So I don't know.
Yeah, just a quick one. Thank you, Stu. I want to respond on the previous question as well. And I think this is where integration with other materials programs can also be very fruitful. And Mama Lee is the DOE program IMMT. She's present on this call, but as part of our roadmap in that program, there is also activities on ion irradiation versus neutron irradiation. So it's an excellent opportunity for us to work together. Thank you.
Thank you, Isabella. We're starting to run out of time here. So if any quick questions, we can get that. Otherwise, we'll start to move to our next speaker. And so maybe I'll start to do that here.
There is one more hand left up.
Oh, Ayub. Okay. I saw it there for a second.
Yeah, this will be really quick, Stu. So
yeah.
So for the need for computational modeling. I was just wondering if this program will be supporting some modeling, especially to understand, let's say, joining or processing of these new materials for cladding, or are you going to rely on NEEMs and other models that are being developed in other programs?
So that's to be exactly decided, but what I could see is that there will be strong, as I pointed out, I mean, there would be strong correlation and collaboration with NEEMs, but if there's some specific modeling that would go directly connected to experimental work, then maybe we would fund some of that when it's got, really has such a strong connection like that. But otherwise, in many cases, we're going to be reliant on strong collaboration with the NEEMS program also. So I think it might be a little bit of both, but in most cases, we're going to be relying on the NEEMS program. So.
All right, thanks.
Yep. All right. Then maybe we'll move to the next talk. Mark, are you there? Do you want to share your screen, or do you?
I am available. Let's see if I can quickly share here and keep rolling.
Okay.
All right. Are you seeing my presentation and it's in full screen?
Yep, that looks good. And so I'm going to pass it off to Mark Albert, who's going to talk to us about a really nice advanced reactor materials development roadmap developed out of EPRI. So go ahead, Mark. Thank you.
Well, thanks, Stu. Thanks for having me. Appreciate the opportunity to speak today. As Stu said, I'm a principal technical leader here at EPRI's Advanced Nuclear Technology Program. And just wanted to give you an overview of our advanced reactor materials development roadmap. A couple clarifiers at the beginning. I certainly won't be going in as much technical detail as Stu did with his excellent examples. This roadmap is kind of high level, but it's intended for audiences maybe at a little bit higher level to start some of the discussion of, what are the materials of need, what are the material combinations. So I think this is a good opportunity to really engage in the community and the stakeholders in, helping to prioritize some of those materials and what are the research gaps that programs like IMARC can help fund. So real quick introduction. I am in, as I said, EPRI's Advanced Nuclear Technology Program that's focused on the deployment of new nuclear. And I lead our research portfolio on advanced manufacturing and materials. And really our goal within the program is identify, develop, qualify, and deploy economical manufacturing, inspection, and new materials that enable, as Stu said, better lifing predictions, improve quality, improve cost, as well as alternative supply chains and reduce lead times. And certainly the three buckets there I described, where today's discussion is obviously focused on our advanced reactor materials development initiative. This audience is well aware, so I won't spend too much time on this slide. But the three big areas or buckets that we see in kind of the challenge of advanced reactor materials and their deployment is certainly codification. When we talk cladding, especially fuel cladding, it may not necessarily need ASME code qualification, but even capturing that in-air test data is a significant effort. And then if we're talking cladding in terms of functional cladding, corrosion resistance on internal wetted surfaces of structural components. So there's not necessarily a structural aspect, but certainly still a codification piece there. We talked about, as Stu mentioned, and Gary and Mike mentioned, the environmental effects and the long lead times to capture irradiation data. And that's not everything, it's corrosion in other areas. And then, the challenge of separate effects versus combined effects. And, what I see as the biggest challenge, not only for IMARC and other development programs, is how do you do testing that is broadly applicable and can be used across reactor design types. That's the biggest challenge, and I see the longest lead time is being able to correlate, irradiation data, but in a molten salt versus a sodium environment as well. And then the big piece that EPRI is really supporting, and I think Stu hit the nail on the head, is we can develop the best material in the world, but if we can't produce it in the product forms needed and the quantities needed, all this research is for nothing. So the supply chain and having that understanding of the informed fabrication and design is really critical. So having that engagement across the supply chain from early R&D in programs like IMARC all the way through the end user that's going to be operating and constructing these plants. Again, this audience is well aware, but here at EPRI, with our owner operators and utilities being a vast majority of our membership, we see all the unanticipated material challenges in first of a kind applications. Obviously, we talked about the new environments and then the fabrication issues for new materials and the high scrap rates or extremely large increases in cost to get very specific, minute specifications. And all that to say, codes and standards specifications are needed and a big piece of this. But what can't be lost on industry is even once you get something codified, the challenge is that those are minimum requirements, and having demonstrations, having a deep understanding of how the fabrication and weldability and joining of these materials really impacts. So I want to underscore the need in materials research during design and continued through fabrication and demonstration is critical in reducing overall project risk as we talk about advanced reactors. So where have we been at EPRI in some of these efforts? We have the advanced reactor materials gap analyses. This was a series of 4 gap analysis focused on the 4 major reactor coolant types. And this was a review of available data that was available to support material implementation into designs, right? So early R&D or existing data for R&D of what candidate materials could be used. And that provided a summary table within these 4 reports that summarized the candidate materials for each reactor type and a summary of what data does and does not exist. So these 4 gap analyses are publicly available. You can search the report numbers once you get the slides on EPRI.com and download those reports. So ultimately, the focus of this was, how do we get to a rational planning and coordinated materials development and validation programs for these advanced reactor designs? So exactly like Steve said, forums like this are helping to inform that exact conversation. And that's where, the roadmap was intended to be a conversation starter and a first effort to go down this path. I will kind of put a caveat that, our road mapping was heavily focused on structural materials and cladding, I'll call functional cladding of wetted surfaces. There was certainly discussion on fuel cladding. HT9, obviously, probably one of the biggest or most researched fuel cladding materials in the past. So I will want to caveat that for this audience today and our topic today. Most of the fuel or the materials discussed are not necessarily fuel related and highly involved because the fuel is often, the proprietary piece for some of these designs. But I still think, coordinated efforts to capture data needed to deploy some of these materials across designs is really beneficial. So all that to say, this road mapping effort, this gap analysis led to EPRI's Advanced Reactor Materials Roadmap. So the Advanced Reactor Roadmap really was broken down into a structure on reactor types, so by coolant type, then the material types. So we have areas for austenitics, ferritic martensitic, the nickel-based alloys, and then some of the other areas of graphite, corrosion needs or data gap analyses, and then cladding. And again, some fuel cladding discussion, but primarily more of a functional cladding for internals and internal wetted surfaces. And as I mentioned earlier, the structure of the roadmap is really broken down into 4 categories. So your in-air properties for codes and standards like ASME, and then your material response in environments, including corrosion and irradiation and those combined effects. And then not to be lost is that confidence of supply chain. Can we actually produce these materials from a laboratory heat sizes to full scale, integrated with plant designs and your major component OEMs, as Stu mentioned. So before I take a deeper dive into the roadmap, because I think that's where most of the panel and the folks on the line today really want to hear is what are the materials or candidate materials. This is our kind of initiative and what EPRI has going and ongoing. So we've done the gap analyses, we identified those gaps and worked them into roadmap priorities. And we're now at the point where we need to, as an industry, have a coordinated materials development and validation effort. Stu and everybody talked earlier of the long lead times and the aggressive deployment timelines of these reactors. So, EPRI really focused on how do we get more coordinated as industry, supporting workshops like the one today. But we've also are in the process of forming a technical advisory group to help really come together as an industry and what testing programs can be done, need to be done to help accelerate the deployment of some of these materials. And to that end, a lot of our research today is really focused on developing those accelerated qualification approaches. So Gary Wasson has work done at University of Michigan, correlating ion to neutron irradiation is a perfect example. Modeling and simulation and where can we take some of advantages of those approaches. And then another area that we have ongoing research is really artificial intelligence and machine learning. I think there's no substitute for physical testing. The models are helpful, but aren't going to get us the full way there. But the real challenge I see is, as I talked about earlier, the combined effects challenge. And what we're really focused on with the artificial intelligence and machine learning is, can we use some of those frameworks to reduce the testing program needs? So instead of doing the full gambit of testing or across all these different combined effects tests, is there a way to correlate some of these data and take a large test matrix that's going to take millions of dollars over 20 years to perform, and can we whittle that down to maybe a smaller subset of testing required to make the most informed decisions for reactor designs and deployments? So all that's well and great, but how do we actually transfer that to industry? And there's a number of ways EPRI is doing that. Certainly code cases, material handbooks, and property databases to inform design decisions, ways to mitigate degradation mechanisms, things like material specifications and guidelines. Again, what is needed above and beyond codes and standards. And then obviously the need for industry test beds and test facilities. Might make a perfect example of, the need for neutron irradiation and fast flux, things like VTR, but also the need for where does industry need to develop test stands for specific testing. And, certainly, folks that have the money will go out and do it on their own. But I think there's a huge opportunity to pool resources and have industry test beds that are accessible, not just to one or two organizations. And then obviously a big piece of the work we're doing is, as I said, on that supply chain and advanced manufacturing demonstrations. So to kind of shift gears and get down into the weeds a little bit, so I have a few screenshots from the Advanced Reactor Materials Development Roadmap. And I'll try to go over these in somewhat detail. Certainly with the time allotted, I don't want to take up too much time. But you can download this roadmap. Again, it is a free public roadmap. You can download with the QR code there, or search EPRI.com on that report number, and that'll come right up. So the roadmap here, this is probably an eye chart, and the next couple of slides have zoomed in versions with more granular detail. But the roadmap, as I said, broken down by reactor types, as well as material types, and then the road mapping section. So within the roadmap section, we have it broken down by austenitics, and I'll go through some of the details here just to kind of maybe get some of the conversation as we go forward. Certainly these are more structural related, but obviously I think for this audience, there's going to be no surprises. 316H and alloy 709, D9 stainless, and EPRI is also doing some work on CF8C+, which is a wrought version of a cast alloy that EPRI is working to get into codes and standards. Has some of the creep properties, comparable to some of the nickel alloys, but down at the cost of, austenitics. Certainly ferritic martensitic on this area and low alloy steels, And this is where I think coming into some of the conversation today brings into the potential need to clad some of these materials as well. Certainly the nickel-based alloys, 800H, 617, and Hastelloy N are of interest as well. Certainly graphite, which I think I'll forego any of that conversation, as graphite's obviously a different beast of a material. But then the corrosion properties, right? And really the need, particularly in molten salt and other environments like lead that are not well understood by industry and don't have a long history of data. And then some of the dissimilar metal weld joints. I know there was a question in that area that was brought up in the chat. Again, these are probably more structural, but grade 91 to stainless steel, 800H to grade 22, and 709 to ferritic martensitic steels are certainly of need. And then lastly, the cladding area. As we talk about some of these high temperature alloys, refractory claddings are certainly a big area of interest. Again, adding some aluminum forming and some of those stainless steels, as well as some nickel-based claddings on top of some of the stainless steels. So I realize that I'm kind of coming up on the end of my time here. As I said, you can download this report. These slides will be available to everyone after the meeting, but kind of broken down in by gas reactors and then different material types. So here's an example of the more granular austenitic stainless steel road mapping, broken down on code properties, irradiation, corrosion campaigns that are needed, and some of that data. So again, very high level for the technical expertise on the lines today, but this is kind of a conversation starter to help guide discussions on where some of these programs need to develop and where we could be more coordinated on capturing the data across industry. Because the last point I'll make is there is a ton of research to be done over numerous years and millions of dollars. And if we can be more coordinated in our effort and combine resources, I think there's a win-win across the board for everyone. So with my closing slides here, I will kind of half plug and half, just let everybody know as part of this coordination, EPRI, we have this expertise in the high temperature arena. We've been supporting the fossil industry for years and have quite a bit of capability in creep and creep fatigue and time dependent properties. And we're really seeing this at EPRI is this convergence of similar needs and challenges across fossil, thermal energy storage and concentrating solar, some of the low carbon initiatives, and nuclear and even fusion. So with that, we've actually assembled an initiative called AM3, which is Advanced Manufacturing Methods and Materials. And no surprise, this is kind of aligned with the DOE's AMMT program. I think we kind of had this kind of similar thought process and, kind of came out with these initiatives or realignment at the same time. So with that initiative, we've actually had a large investment in our laboratories and material characterization and testing, a lot of additional creep and creep fatigue frames, and a lot of material microstructure characterization capability has been added to our facilities. So wouldn't be anything without a shameless plug here at the end, but all to say, this is where leveraging test facilities and these capabilities is important, and making sure that we have the test facilities needed to enable some of these deployments. So with that, I'll kind of wrap things up and turn things over back to Stu.
Okay, Mark, thank you very much. That was really a nice overview of a really nice roadmap that's been developed by EPRI, and it was really neat to see the capabilities that you're building up too. So that was excellent. And I know we're running out of time here, but Cheng had his hand up for a while. If Cheng, did you have a quick question or?
Yeah, it's one quick question for Mark. I guess I downloaded the roadmap as soon as you showed it, and then it looks like the roadmap is based on specific reactor designs, with kind of specific coolants and structural materials in place. I was just wondering, because the devil's always in the details, wondering if there's any guidance as a result of your program that can kind of group certain materials together. I'm just wondering, like the work you're doing on, for example, fluoride salt, corrosion on 316, like will your results have some impact on, for example, chloride corrosion on 316 as well? Similar question on, your work on binary, iron 9 chrome, does that extend to T91? Iron, 12 chrome, does that extend to HT9? Because I think the industry, at least our reactor designers, will find some of these data for materials that are similar and we assume would behave similarly, but we can't use the data as is because it's not exactly the same. Does that question kind of make sense?
Yeah, and honestly, I think it's the biggest challenge that we have as an industry. I mean, and DOE, I think, has the same challenge, right? Is how do you fund programs that are broadly applicable with the realization that there is a need for testing in specific environments, specific DPAs, and even specific salt chemistry. So yeah, the roadmap is probably a little bit high level for that conversation. I think a lot of the work we're doing is how do we leverage our funding to make sure that the testing is applicable to the most stakeholders, but at the same time valuable, right? Because it doesn't make sense to do a test that trying to make it broadly applicable, but then it becomes less valuable for anyone. And that's work where some of our AI and machine learning framework that we're trying to develop is really focused on getting down to answering some of those questions of what tests could be most applicable for a chloride and fluoride salt or across reactor types. So I don't know that directly answers your question because I think it's an unanswered challenge, and I think it's something that I'd like to input from this group is how do we get better aligned in understanding that rather than every organization going out and doing their own testing, how can we pool resources to do testing that's beneficial to a broader audience?
So thank you, Mark. I think that's actually a good area to talk about at the end as we're starting to get more input from others on the different material classes and the different testing that we need. So thank you again, Mark. And I think we'll move on to the next talk by Farshid. Is it Shiroki? Hopefully I got your name right.
That's correct. That's correct, Stu.
Oh,
let me try to share my screen and I will get started here.
Okay.
Can you see my screen?
It's almost there. Okay. Yep. If you put it in full screen mode, I think we'll should be there.
Okay. Okay.
It's moving slowly, but yeah, I don't see full
right.
screen mode yet, but unless do you have a double monitor? Is it possible that?
No, I have a single monitor.
Okay. Huh. Well, it's not showing in full screen, but I can see your slide well enough if you want to just go ahead and continue. I think
it is in full screen and on my screen anyway.
Okay. Well, go ahead.
All right. I'm Farshid Shiroki. I work for Framatome Inc. in the United States. I am director of our high temperature reactor technology. And this presentation was supposed to be given at Sun Valley, but I wasn't able to attend that ANS meeting. So I was given the opportunity to present today. Framatome is obviously involved in a variety of reactor technologies, but today I'm focused on our high temperature reactors. Mainly our steam cycle high temperature reactor on the right. It's a Rankine cycle. We'll go to a little bit of details on that. And on the left is our very high temperature reactor, which is a Brayton cycle. Yes.
Your slide is actually not even moving forward, so we're still on your first slide.
Okay. So maybe it's better you have my presentation. So maybe it's better for you to drive the presentation.
Teresa,
So
can
I'm going
you?
to stop. Pardon me?
Yeah, I think Teresa has it, or Holly. Teresa or Holly, can you?
I'm ready as soon as you quit sharing.
Okay.
Okay, I have stopped sharing.
Do you see the full screen there?
Yes.
So I don't know. You want
Okay,
to
just go. Thank you. Go to the next slide, please. So I'm here today to talk about the high temperature gas cooled reactor technologies only. On the left is our thermal spectrum high temperature reactor. On the left is our also a thermal spectrum, but the very high temperature gas cooled reactor. So next slide, please. So Framatome has been involved in developing high temperature reactors since early 60s through our predecessor companies, starting with the German AVR pebble bed reactors and HCR module back in the 60s, 70s, and 80s. And in the early 90s and in the 90s and 2000s, we were partnered with General Atomics and Russian Federation on the GTMHR project. And then in mid 2000s, we started working on our VHTRs, codename Antares. It was a 600 megawatt prismatic core, indirect cycle, combined gas turbine generation. It had a core outlet temperature about 850 degrees C, and is doved into the NGMP project back in the late 2000s. So we were one of the three teams that were developing in our initial design of the high temperature gas cooled reactors. So based on that background, we ran into some issues, material issues that I will discuss a little later. And so we sort of stepped back and looked at a steam cycle, a lower core outlet temperature. So the material needs of the steam cycle high temperature reactor with the core outlet temperature of 750 is much less than our VHTR. So we step back, and the market's still there because the market for our reactor is processed steam, and there's plenty market for processed steam at these temperature ranges. So our reference design is a 4-module, 625 megawatt thermal each module. That's our reference design. Later on, since the late in the 2010 timeframe, we understood that folks were interested in lower powered reactors. So we have a family of steam cycle high temperature reactors. Our 625 has 2 steam generators. We have a 315 megawatt single steam generator design. And for our European customers, they are interested in steam only. So we have a 180 megawatt design. And later for our remote sites, we looked at that market also, a 54 megawatt, and then we have a micro version and a mobile version. So the key here is all of them use the same fuel block, prismatic fuel block. They all have the same fuel and the same fuel block. It's just a number of fuel blocks different, and the configuration, of course, is smaller. So that's our family of our HTR at this moment. We are funded by internal funding, R&D funding, and so we are looking for customers and to further develop it and get in front of the NRC for licensing. Well, our licensing strategy is basically set since the NGMP timeframe, Part 50, and nowadays we're going to be doing this new follow the risk-informed performance base option of the Part 50 and 52, which is per NEI 1804 standard or NEI 1804 guidance. Next slide, please. So our 625 is again it's a cogeneration. It produces electricity and process steam, and it's mainly designed for process steam. You know, the steam market, the process heat market is captured to natural gas and fossil fuels, and of course electricity can be produced by even light water reactors. So we're not in the market to compete with electricity, because our reactor is the fuel for our reactor is more expensive, as it uses triso particle fuel. And although we have a 43% net efficiency, still the steam is the electricity unit price is pretty high. Our core inlet is 325, core outlet is 750, and we can produce steam at 566 degrees C. And there's plenty of market for that on both U.S. and overseas, and of course the safety that afforded to us by triso particle fuel allows us to co-locate it near the actual applications, which most of the steam users currently have basically their natural gas steam plants right on their plants. So we're in the conceptual design phase on this reactor, and once we find a serious first customer, I mean, it's very difficult to find the serious first customer. We're ready to get into the basic design and interactions with NRC. Next slide, please. This slide shows our VHTR. This was actually, we started up looking at this design back in, like I said earlier, in mid 2000s. It's a core outlet temperature of 850. It can go higher, and it has a intermediate. It had an intermediate heat exchanger. The secondary side originally was a gas cycle, and that's when we ran into some issues with our IHX. We could not design or come up with materials that does the gas-to-gas heat exchanger at these temperatures that would last any period of time. We looked at compact heat exchangers, variety of compact heat exchangers, and that's where we actually put this design on ice for a while to find out what we can do to coming up with this. The primary side was fine, but this heat exchanger, the intermediate heat exchanger, was difficult for us to come up with a design. More recently, in the past couple of years, we're looking at the salt secondary. And then I can talk about that in a little bit of what issues we have with the salt secondary. Of course, originally it had a gas turbine for electricity generation on the secondary side, and also process heat at variety of temperatures depending on and on the tertiary side we had a steam generator, and then the standard Rankine cycle for on the same shaft actually to produce electricity. At full electricity mode, it was 290 megawatt of electricity at about 49% net efficiency for this reactor. Of course, we could get steam process heat out. In this case, there's not steam anymore. It's process heat out up to around 800 degrees C, which is quite a bit of market there. In that area, currently being catered by natural gas. Next slide, please. So this is the real slide for this particular venue here. The material construction for these two types of reactors. The black items are materials that are available now, and the red are that requires codification and development. For our steam cycle, most of our materials are available. Our fuels, obviously, UCO kernel tricycle particle fuel. It's been characterized and information being taken out over the last 20, 25 years under the AGR program. Our graphite is, we have several graphite types, SGL carbon, MBG 17, and Toyo Tanso 110 is our graphite of choice for both reactor types, our steam cycle and our very high temperature. For our vessel system, both reactor vessel and steam generator vessel and a cross vessel, which connects the two of these vessels together. For our steam cycle, we have a standard PWR steel SA508, 533 that doesn't even need cladding as our light wire reactors need. But our very high temperature reactor, we need a 9 chrome 1 moly. And although this is pretty much codified and available, the supply chain for this is limited. The thick section welding of this material is difficult, and we're looking at it ourselves. And of course, that's where it's in red. This is not something that we can do right away. It's hard to find the bulk this material. Our reactor internals is alloy 800H and graphite. Obviously, we've worked with the NRC, and Div 5 is in the ASME, and NRC is accepting that now as we talk. And for our steam generator, we have our tube type steam generator for our steam cycle has a alloy 800 section and a 2 1/4 chrome 1 moly section. So because of the price of alloy 800H, so we had divided the higher temperature side of the steam generator is 800H, and the lower temperature side is 2 1/4 chrome. Of course, that provides that gives us a problem of dissimilar weld of these two, and we've been working on that. That's probably the issue there. But we have some designs that actually takes that section out of the steam generator proper and have more access to it for inspection. The need that we have is the intermediate heat exchanger for our very high temperature reactor. We're looking at a ceramic heat exchangers, ceramic silicon carbide, mainly ceramic tubing, ceramic material, and that's really the key there to try to come up with a steam generator or heat exchanger in this case, not a steam generator anymore. The heat exchanger that has a gas to molten salt heat exchanger with the ceramic internals, tubing or other configurations. Of course, instrumentation control is standard. In our decay heat removal is basically all passive. It's a water-based decay heat removal. Circulators are standard circulator and is available today at the power levels that we want. And the reactor building is basically concrete. It is a deep silo type reactor building. So that's one of the things that we're considering to lower the or not have the silo so deep by changing a design. We're looking at a design that the steam generator is not below the reactor vessel. In that configuration, the silo is very deep. It's almost 47, 48 meters deep, and that's expensive to build. That's one of the biggest expenses. So we're looking at the designs that the steam generator is parallel with the reactor vessel. So that there is some challenges there. Of course, our refueling machine, our refueling of these reactors is remote and computer controlled. So it's been done before. So Fort St. Vrain had it, and technology, or remote technology, computer technology has advanced quite a bit since 30 years ago. So we're pretty confident that our refueling machine would operate by moving the fuel around and refuel the reactor every so often. For us, is about 18 to 24 month refueling cycle. So mainly the takeaway from this is the non-chrome moly and ceramic material is really what our needs are as far as additional research that needed for our advanced high temperature gas cooled reactors. Next slide, please. So these next two slides is basically tells you the temperature ranges that the industry needs as far as process heat is concerned. Like I said, we're not electricity is a byproduct. I mean, we can load switch but our main goal for this reactor concept is producing a process heat for the industry, and these are various temperature ranges and various reactor types. The first one is the light water reactors. Of course, that's a very low temperature, and then our steam cycle it can cater to a variety of steam users. There's quite a bit of demand already exists there, and if we can and with the safety of our reactor, we can basically co-locate these with the steam users. And our VHTR is the Antares is again goes up to around 800 degrees C, and there is plenty for it there. And that design can actually that the fuel can withstand, the graphite can withstand the very, very high temperature reactor, which goes up to around 1000 degrees C. But that's something for many years from now. So the possibility of advancement is there, or stepwise increase of the core outlet temperature, and the design is there. Next slide, please. So this is basically, it says how we're going to do this. So it's basically divide and conquer. We looked at our VHTR, and the same fuel for VHTR is used for HTR, and the same siting, same licensing process, same safety case is for designs. But of course, the last three items, the high temperature materials and the heat exchanger and the very high temperature process interfaces are issues that our next generation or higher temperature version of our reactor is designed for. So our strategy, our I guess commercialization strategy is to work on the steam cycle SCGR, and then with a view that there is life after steam, this lower temperature, if you could consider 750 degree low temperature, there's a life after that, but there are some research needs that type of reactor needs. I think that's all I have, and I'm open to questions.
Okay, thank you, Farshid. And I should note, I mean, this really was a nice overview of high temperature reactor concepts that you're looking at, but it also did point out areas that, and I should have stated this from the beginning, there are some areas clearly that in your presentation and in Mark's presentation that wouldn't be covered under IMARC, but maybe be covered under AMMT. But the importance of this was to see where are your needs, and so I think that was really useful. And thank you. And are there any questions? I actually don't see any questions. We're running a little behind, so maybe what we'll do is move on to the next presentation. So thank you again, Farshid. And then I'll see if I'm successful to share my screen again here. Let's see. Okay, and put that in. All right, can everybody see that? Oh, maybe right before Robert, did you have a quick question then, or? I see Robert Davis has his hand up. Okay. Well, I'm not hearing anything from Robert, but we're going to have some time after this presentation for other discussions. So Robert, if you want to put your question in the chat, we'll get to that right after I go through a little bit of a summary of the contributions to the GAIN Innovative Materials Workshop at ANS. So I know many of you weren't able to attend that meeting. So what I wanted to do was give a little bit of an overview of the industry needs, and then a little bit on some of the other talks that were given at that workshop. Of course, I'm not going to discuss this in detail, or else I would take the whole time just to just give this summary. So I'll try and get a nice quick summary, and clearly if there's anything that I incorrectly say, please let me know. So this was a nice overview, nice workshop that we held at ANS so that we could actually get some face-to-face discussion. And I think what we really got out of this was some really nice overviews from the different industry concepts from Oklo, Westinghouse, and TerraPower, and then a few overview slides of different national lab capabilities and university work that was discussed in. So I'm going to mainly spend my time on the nuclear industry needs, because I think that's really directly related to this program, and then a little bit on some of the other capabilities that were discussed afterwards. So on a high level need, there was a nice overview from Simon Pimblott on sort of high level needs for high dose irradiation of materials. And clearly one of the things pointed out, as we've already said a couple of times here, is we need an irradiation testing facility in the US. Clearly that would be useful to many, if not all of these reactor concepts. We also do, if we want to have new advanced materials for either structural or cladding, we need to be able to qualify those materials in short time frames. If it's going to take 20 to 25 years, that's going to be really difficult for us to get these new materials, so hopefully into new reactors. So hopefully we can shorten that time a little bit. And in order to do that, we're going to have to prioritize the immediate needs, and that's why we're having these workshops is to try and get a good idea of what are your needs and try and center this program to cover those. And so, overall, a new material program addressing these, I think, would be really useful. So let me start with the first Oklo's Aurora reactor. That's a sodium-cooled fast reactor. Ryan Webster gave a nice overview of this reactor design. Its electrical capacity is 1 to 15 megawatt electric, thermal capacity up to 50 megawatt thermal. Usable heat is in the 500 to 550 C range, a capacity factor of greater than 90%, and licensed operating life of over 20, so 20 plus years, and it's a small reactor. It needs less than about an acre for a reactor like this. But there are larger designs in development, but what he sort of went over was the smaller reactor design that they're trying to push forward. And what he did really nicely was went over their needs. What are their materials needs for these cladding and core materials for this reactor concept? In the near term, they just need the existing alloys. So they need the existing alloys that have a large amount of radiation history on them. So that's ferritic martensitic or austenitic stainless steels. And even those, if it's HT9, for example, they are challenged by limited supply chain capacity. It's not actually easy to get all of your components made in these materials right now. So that's one of the things they have to address even right from the beginning. And that's not something that we would cover in IMARC, but I think that's important. That's for them in the near term, they need that. But in the intermediate term is where we sort of get into areas that I think this program could address in the future, and that's in the sort of the 5 to 10 year time frame. Can they develop better FCCI barriers for these materials? So adding the FCCI barriers is really important to them. can they make incremental improvement in the existing alloys to either make better ferritic martensitic steels or make some improvements in austenitic alloys? And then can they even look at some commercial availability of some new alloys? So that might be a refractory based metal alloy, maybe it's something else. So they are looking at some new materials in the 5 to 10 year time frame. There's a large challenge there, because most of these, when you add even incremental improvement in some of these existing alloys, there's really not a lot of high dose performance data on those materials. And clearly, if they want to get those made and make a large number of cladding tubes out of that material, supply chain development is something that would be difficult. So that's clearly going to be an issue that we'll need to work with, is getting industry back up and interested in making some of these new materials. And the longer term is now where they want to have more radiation tolerant materials. We have the oxide dispersion strengthened alloys that they're interested in, and even new manufacturing methods to make a material in a less expensive manner, or make a new material in a tube form that could make it so that it could apply to a high dose reactor cladding. And they're also looking at even advanced fuel forms. And so if you start looking at different fuel forms, you may run into different fuel clad chemical interaction. So that's where maybe a new cladding may have to go along with that advanced fuel form. And same thing as even in the intermediate term and the long term, they're really challenged by lack of performance data. And in many of these, there's even limited to even no existing supply chain. So that would clearly be important if they're going to move to some of these advanced materials. So the next talk that was given in that workshop was by Westinghouse on their lead fast reactor by Mr. Tatley at Westinghouse, and he nicely started with a good overview of their design parameters. Reactor power a bit larger than the one I just talked about, a 450 megawatt electric heat output, and efficiency of up to 47%. So really good. And the primary coolant is liquid lead. The secondary coolant would be a supercritical water coolant. And the nice thing about this reactor concept, the ultimate heat sink is to the atmosphere. So it actually doesn't need to be next to a river or something like that. No water body is actually needed for ultimate heat sink of this reactor. It is load following through a thermal energy storage system. The reference fuel cycle is open, but it could support a closed fuel cycle. The fuel type is just oxide fuel in phase 1, but in phase 2, they may also be looking for different fuel, maybe uranium nitride. Cycle length and refueling is long as 8 to 15 years, and is direct to cask refueling. Operating pressure, which is one of the nice things about the lead reactors, is quite low. It's only 0.1 megapascal. With their supercritical water, it's higher on the secondary. It's at 34 megapascal on the secondary. And the lead coolant min-max temperature, in the phase 1, it's at the lower temperature reactor type. So it's 390 inlet, but 530 outlet. But in phase 2, they want to even push the higher temperatures, where you get into perhaps some other either stringent creep issues, or even lead corrosion issues of going to higher temperatures. So there they'd like to go up to 650 degrees C in phase 2. So what materials are they looking at? Just like in the Oklo design, at lower temperature in phase 1, they're looking at using existing qualified materials with coatings. So 316L may be the one that they just start with. Another material that has a lot of, especially in Europe, has a lot of experience as a cladding is 15 chrome, 15 nickel Ti, so 1515 Ti. So it's also called very similar to AIM-1, which they use in Europe, or they used in Europe for the Phoenix reactors. So that these are sort of their base materials that do have a lot of irradiation experience, but they would have to be used probably with a coating and cladding. And a nice table is shown here to the right with the candidate materials for the guard vessel, reactor internals, the fuel rod cladding. You know, there is where the 1515 Ti is with a coating. But in phase 2, would they go to higher temperature, then they would want to qualify new materials for greater reliability at the higher temperatures. So maybe it's austenitic forming or alumina forming austenitics or FECROL or ODS with a cladding. So a more radiation tolerant cladding, but with a coating on it to prevent corrosion, or even going up to a 6-SIC in the end. So they're really pushing to the materials that we in the IMARC program, I think that we would want to be able to address for better radiation tolerance and better corrosion resistance in those materials. So that's a nice overview of a sodium fast reactor as well as a lead fast reactor. And then what we got was a nice overview from TerraPower on their molten chloride fast reactor with Cheng Zhu and Matt Wargon were the authors, presenters of this. Their program is focused on materials testing for design analysis, as well as leveraging that materials testing for NRC licensing and qualification. They have a lot of materials of interest. In general, the first materials are nickel-based materials, alloy 625 and alloy 617. So these are their preferred materials because of their known high temperature performance. They know a bit about their corrosion performance. They're weldable, and they do have an ASME code case. But some other materials are 316H, most probably with a coating, or maybe even in the future, they can go to even refractory alloys or ceramics. And so there's, once again, areas where I think this program could really help out. But there's a lot of engineering properties that they need for these materials, especially if they're running at high temperature. You can see they want to go from 550 up to 800 degrees C, so quite high temperature. And at those temperatures, creep, fatigue, corrosion, and erosion are all areas of where they really need information on those materials. And then on top of that, they need radiation effects on their mechanical properties at those temperatures. And that's in the sort of 0 to 100 dPa fast spectrum area. So, so that sort of summarized 3 advanced reactor industry needs talks that were given. And if you want more detail, they're actually already on the GAIN website, so you can pull those down from the GAIN website. There are also some nice overview talks on university and national lab capabilities and methods. I talked about it a little bit in the beginning, but the capability needs for irradiated and radioactive material, that overview was given by Simon Pimblott from INL. There was also some work on where we could develop advanced ODS alloys, some of the research that has already been done, and some of the routes needed for applying it for these materials were given by TSBUN at Oak Ridge. And then more related to the high dose irradiation testing, if we're going to do that with ion radiation, there was a nice overview of some nanoscale mechanical testing techniques by Sid Patak at Iowa State University. And then finally, there was a nice overview on actually the program that we've already talked to you about a couple times in some of the questions, is a high dose ion radiation program led by Gary Waz that's been going on for the last 6 years. A nice overview of that program was given by Kevin Field. So I didn't have time to do all the detail on those. I wanted to center on the industry needs, and hopefully that was helpful to you. I do have some time now for some questions before we get into the different materials areas. So let me see if I can make sure I got the chat. Yes, the chat does have any questions.
Stuart?
Yeah.
Farshid, Robert Davis did put his question in, and
Oh,
I
okay.
had sent it back to Farshid, and the question was, have any of the potential end users for reactors to supply process heat, such as Exxon, shown any interest in having a high temperature reactor at one of their facilities? And Farshid replied, he had to jump off the call, but he
Oh,
said
okay.
that the short answer is no, as long as natural gas is cheap and available, the process heat users will not buy a reactor. Today, the landscape has changed, but we're still looking for a first adopter and demonstration of our design.
Okay. All right. Thank you on that. Anybody else have any questions before we get into this different materials areas, which I definitely would like to have your input on. So I don't see any hands up, don't see anything in the chat. So maybe I'll just go ahead and move forward. And mainly what I want to do here is just, I think I might be blocking this. Okay. Just give you lead in for the different areas. So as you, I mean, if you have the agenda in front of you, you can see the different material categories that I want to cover, starting with the initial category of innovative metal alloys. So that's one area where we'd like to see development of better materials for advanced reactor cladding applications. And that can include a range of different materials, from a sort of large improvements in advanced ferritic martensitic alloys. So what can we do? What can we develop that's better than HT9, that maybe addresses some of the low temperature embrittlement issues of HT9 or high temperature creep properties? Or can we develop better, or can we develop better advanced austenitic alloys that can address some of the corrosion needs for lead fast reactor, or like the alumina forming austenitics? Are there ways that we can develop refractory metal alloys that still maintain good ductility that could be used maybe in the highly corrosive molten salt reactor or other applications? And then a large area that is being explored now, but is largely unexplored, is the high entropy alloys, and that can have a range of different alloy contents in it. They don't all, I'm not saying they all apply to nuclear. Don't think that I'm saying that, but maybe there's some specific alloys that could have some specific application that do maintain good ductility and can also maintain have a good, excellent radiation tolerance. But with all of these, we need to develop novel microstructures in those. So could it be an advanced ferritic martensitic alloy that has a nanostructured grain size that can give it the radiation tolerance, a better radiation tolerance than what they have right now, but it has to be able to also be stable? Can we have novel manufacturing techniques for these materials to produce the thin-walled tubes in a fairly inexpensive manner, but then makes a good quality long tubing? We need to have joining methods for these advanced alloys, and it may be more difficult for one alloy versus another, and one joining method may not work for one and it may work for another, of course. And then, of course, coating methods to prevent, or I mean, we either are developing an advanced alloy that already prevents FCCI, or are there coating methods so we can coat the inside of these materials for improved resistance to FCCI. So I'm going to stop after each one of these slides and allow input for others. Are there other alloy areas or manufacturing methods that you think that I'm missing, that you might want to point out to me? Please either put it in the chat or raise your hand if you have anything to add here, Otherwise, we'll move on to the next category. So it might be that I just covered it so well.
There is one question here.
Yep.
What is the effect of the recent SC ruling that limits EPA authority to set climate standards for power plants, for nuclear power plants?
Yeah, I did see that the Supreme Court ruled that. I don't know exactly what effect that will have. That's an interesting point, but will it make it easier for the present power plants to continue with their emitting the same carbon levels into the atmosphere? I don't know. That's an interesting point. I don't know. We'll have to see. Javier, I see your hands up.
Yeah, I just want to make one comment to look at possibilities on the other side of surface engineering, which is the environment side. And we were able to develop a material that is really good on irradiation resistance and general mechanical properties, but is not very good with the environment, be it sodium or salt or whatever it is, or lead. Then surface engineering of that side would be interesting to consider as well. Coatings.
Okay, yeah. So yeah, I mean, I did cover that a little bit on the FCCI side, but correct, yeah, on the outside, it may also be that we could add a coating, or maybe it's, like you said, maybe it's, I mean, there have been studies that showed, for example, in lead corrosion, that varying the microstructure at that surface can help improve the corrosion resistance. So it may not just be a coating, it may just be a way of you're engineering the microstructure on that surface also. So
right.
Thank you. And yes, will you cover functionally graded material systems? So yeah, I can see clearly, and just sort of what Javier just pointed out, Raj. Yes, I can see clearly that a functionally graded surface might lead to better corrosion resistance on the outside, where we don't need that outer coating for structural strength or for radiation tolerance or something like that. So maybe there's a way to functionally grade to get to a surface that's better and more corrosion resistant. So yeah, good point. And I think I'll add that. So.
Stu, I have another comment quick.
Yeah.
Kind of reinforcing that you mentioning thin wall tubes. I think that paradigm of thin wall tubes is going to stay for many years, and is going to stay for many of the advanced reactors. Some people are working on other geometries, but I think that making something as a thin wall tube will be a need for decades, I think, unless anyone wants to challenge that assertion. So that becomes a very important design premise for any material. And I want to bring, for instance, the experience that we have had on accident tolerant fuel, developing ceramics as a thin wall tube. That's one of the major challenges that we have had, and hermeticity and other things. So yeah, I just want to kind of underline that one thing, and I would like to hear from other people as well.
Yeah, thank you, Javier. And I mean, that's an underlying, you're going to see that on every single one of these categories. That's an underlying need for any of these materials being applied for cladding applications. We need to be able to make it into a thin walled tube that's uniform across a pretty long length, depending on the reactor type. So we'll cover some of that more in the next category. So maybe I'll just go ahead and move on to the next category, which is a sort of a sister to the previous category. It's oxide dispersion strengthened alloys. So these are metal alloys, but that have oxide dispersion strengthening. There's a lot of research previously on developing those materials, but there's still our needs for easy or economically favorable methods of making these, making these alloys into thin-walled tubes. So that's clearly one of the issues for oxide dispersion strength of seals. There's a lot of nice data. If you can make a fine dispersion that's uniform in the material, there's a lot of nice data that shows that they have excellent and incredible radiation tolerance, but these need to be made into thin-walled tubes if it's a ferritic steel. And perhaps also there's the ODS fee crawl. Maybe there's that could have a real application in lead reactor or lead fast reactors, but a lot of the initial materials like Ma956 and PM2000 don't really have much of a fine oxide dispersion. So they don't have the 2 to 3 nanometer oxide size. These are 5 to 10 or even larger nanometer oxide, and so not as high a density as what you can get in the 14YWT. So that really makes it not as advantageous from a radiation tolerance standpoint. So can we address that to make ODS V-crawl, but with the fine oxide dispersion? And also oxide dispersion strengthening to austenitic alloys. That could maybe you can take 316L, which we know has high void swelling rates at intermediate sort of 400 to 500 C temperature range. Can we add it? Can we make it with an oxide dispersion that can actually make the void swelling, address the void swelling concern, and still then have a lot of the other benefits of austenitic alloys like ductility and other things, or ease of making it into tube form? So ODS austenitic alloys would be in this area as well. And this, as pointed out in the last area, processing methods to produce thin-walled tubes is critical and very difficult for these, especially some of the high-strength ODS ferritic alloys. Making it in a uniform and fine, stable oxide dispersion is important. And then you get to the joining methods, which the joining methods for thin-walled tubing is really critical. And I just saw Raj, and that's an important point. And I didn't specifically put it on here because I just called it ODS austenitic alloys, but ODS nickel-based alloys would also fit into this area as well. So a little bit even higher nickel also fits into this area if a nickel-based alloy fits well into that reactor concept. Yes, ODS nickel-based alloys could really be an improvement, maybe in radiation tolerance, but also in better high temperature strength. And then if needed, unless the material itself prevents FCCI, if needed, coating methods to coat it on the inside as well. So I've seen a little bit of input already on that. We have a couple minutes for other input on the ODS oxide dispersion strengthened alloys area. Anybody else want to either comment or add something to the chat?
This is Raj Iyengar from the NRC. Can I
hi.
take 30 minutes of your time? I think you've done an awesome job so far outlining all these. Yes, so I think the ODS has, as the technical community well knows, the work from Tennessee and Oak Ridge, it has a lot of promise. With the inclusion of advanced manufacturing techniques, I think it's probably more viable. I did want to mention here, potentially there might be some considerations for using different material systems, not just like a coating, but functionally graded. Just saying, when you have these advanced manufacturing techniques, such as even the additive 3D printing, it really allows more easily for you to change the chemistry or composition and thereby the microstructure throughout the coating cladding thickness to really leverage some of the things that we have not we have faced in terms of operational history. I don't know how much of thought has gotten into that. I think it is probably difficult commercially, but if we can manufacture 3D printing for these systems, these alloys, I think we can still do very well by manipulating that to our advantage. So, can you comment on how much thought has gone into this? I've seen some work from University of Tennessee and some proposals from. Yeah, go ahead. Sorry.
Yeah, no, absolutely. I should point out that advanced manufacturing techniques, especially for the ODS materials, could be a real benefit, but it's also a real difficult problem. There are a lot of groups that are looking into this, but if you have any of the sort of direct energy deposition or laser powder base or selected laser melting, SLM type techniques, either one of those where it goes through melting, it's very difficult to maintain this fine oxide dispersion after it goes through that melting step. So, and I'm not saying you can't get there, but definitely a lot of people are trying, and it's a difficult thing to keep a 2 to 3 nanometer oxide as you do that. But if you can, it can help you in maybe making a duct of this material, or even making cladding. Cladding is more difficult because it's such thin walled. So you might still have to do some extrusion or something like that, or some final sort of reaming or something of the tubing, if after you did a advanced manufacturing technique of making it. So but the nice thing about that, if you can do it through additive manufacturing or some advanced manufacturing technique, is that you might be able to skip the real difficult step of pilger processing into tube form for that alloy, which has been preventing using ODS alloys in some previous applications. So yes, that is important. And I think something that would be looked at in this program. I also see that this program would have a strong complementary connection to the AMMT program, where they're also interested in looking at that also. So, but we would just have to do that so we could make it into a very thin-walled tube form. I think Cheng had his hand up, and I think had a question. Molten chloride fast reactor will be curious about whether ODS can mitigate helium enrittlement issue at high temperature and nickel-based alloys. There's a lot of radiation data. Yeah, so right, so that's true. For the molten chloride fast reactor, if we can develop an ODS nickel-based alloy, can that fine oxide dispersion help mitigate helium, which we know is made in these nickel-based alloys under radiation, to help address that issue, which is an important issue. So that's a good connection and need. Let me, I think, move to the next one. Thank you for all the input here. The next area is ceramics or ceramic composite materials. This is an area that really needs a lot of research to be able to make either 6-SiC or some other composite in a thin walled tube form that's hermetically sealed. That's a real challenge. Just making the tube so it doesn't have any leaks in it or cracks in it is one challenge, but the other is making sure that you join the end of it in a method that makes the whole tube hermetically sealed. So there's a lot of work that's needed in these composite, whether it's 6-SiC or other composites, to produce it in a thin wall tubing. That's a real challenge, and produce methods of joining that. But maybe there's advanced manufacturing techniques that can help us get there. I don't know, but this is very specific to a thin walled tube in these applications, though. And how are we doing on time? So we're still okay on time, but anybody want to make any comments about the ceramic composites areas? So I don't see any comments, so maybe I'll move over to the last area. And this is this last area is really critical, and let me also point out that the reason why I'm trying to get your input is to make sure we cover everything in these areas. I should also note, though, that these slides are going to be available online, and if you look at it and there is something that's missing, please don't hesitate to send an email to me or Sue so that we can get that input in for these different material categories. But clearly, if we're going to develop materials for that are qualified to very high radiation doses, there's a lot of different innovative testing and characterization methods that will need to be improved. I mean, they're not that they're not out there, but improved and qualified to get good data from either high dose ion radiations or from doing microscale mechanical testing. And I connect those two, but I should also say that if we can apply microscale mechanical testing to neutron irradiated materials, that is a help as well, because of course, after irradiation, these materials are highly radioactive. And so we can work with smaller amounts of material and keep the dose down. There's a lot more that we can do with characterizing and testing those materials. And then it does take a long time to do these irradiations. And also sometimes it's very important to be able to measure that property under irradiation. So in situ, maybe creep. We did point out in some of the industry needs that fatigue was a need for some of the molten salt chloride reactors. Fatigue is a very difficult measurement to make even after irradiation, but it's really not that applicable after. It's really something that has to be done in situ. So in situ creep and in situ fatigue measurements under irradiation is really a critical measurement that I don't even know anybody that's doing it. I know there was some that they had done at one time on the SynQ facility back a long time ago, but it's a very difficult measurement to make and very difficult to do in reactors. So those techniques, developing those for either being able to do them at very small scale or being able to do them under irradiation is a difficult and challenging, but would be really helpful in developing these materials. And then, we're getting to better characterization techniques, CT X-ray techniques or X-ray CT techniques can really help us with looking at materials made by different advanced manufacturing techniques, but can they also help us with maybe following radiation damage in situ, or can other techniques help us to follow radiation damage in situ so we don't have to go through some destructive technique to look at it. So there's a bunch of areas there that could be really helpful and help us to, it can help us to qualify these materials faster and also be able to test them under the right conditions, which is really critical, especially with some of these extreme environments. So I see Cheng, you've got your hand up. Did you have something you wanted to add?
Yeah, just a comment. I think one of the major challenges, there is no standardized way of doing these very novel, unique, like the data is very informative for reactor designers. The issue is we can't be sure that when we put it in our safety case, and go through our QA, all these tests are done on fuel cladding, which, typically is, safety class. And there's a slew of additional requirements, regulatory and quality assurance that they have to go through. And the challenge has always been that, yes, we have, all these irradiation, these cool characterization measures and data from it, but when we present it to the NRC, they might just say, hey, this is not applicable. I guess my question is, since we have NRC representatives here, is there any push to, or some way or some path for us to get these, novel testing methods to be qualified for use for an eventual licensing application?
So I don't know if there's anybody from NRC on this webinar.
Okay.
But if there is, please chime in. But I would just say that I completely agree with you that being able to standardize these small scale techniques to show that they provide data that links to large scale testing is critical in these different measurements. So, whether it's making sure that you're testing across enough grains, or making sure that the orientation so that you can correlate that measurement with the grain orientation. All of those have to be looked at depending on what the size and scale is, because some of these micro scale techniques covers a lot of area. Micro scale could be 1 to 2 micron with fibbed out specimens, or it could be it could be 100 micron femtosecond laser cut specimen. So the 100 micron may be able to, on a nanoscale material, might be able to cover multiple grains across the tensile cross section or something like that. So yes, those are things I think that need to be looked at when we're looking at new in situ mechanical testing techniques, because they need to be able to apply to or as close as possible to an ASTM standard. I should also point out, though, that one of the things that Gary Waz's group has been doing in their ion irradiation testing is they will be leading to improvements. There is an ASTM standard out for ion radiations, but maybe you don't know that, but there is one. But they will be looking to improve that ASTM standard as one of the last milestones in their program right now. So I think that in itself will be helpful as well, if we're going to be using that for continued ion radiation testing also. And Arun, well, actually we got 2 comments here. Let me start with Osmond's. Osmond, you said it. Yeah.
Bob Davis with NRC has his hand up. He might be able to answer that original question.
All right, but before I get into those questions, let me let Bob talk then.
Thank you.
Okay. Okay, so now you can hear me. I had problems with my mic before. So I had to step away for a minute, and then I came back and I see this last slide, but I heard somebody mention fuels, and then I guess there's kind of 2 paths. One path would be to develop or change some type of have some type of a ASTM standard, and then eventually that would be, I guess, when somebody submits an application, that would be looked at. And I'd say a very good way of doing it is to say if there is an advanced reactor that the folks which there are several, that people are in contact with the NRC. Currently, I am not in the advanced reactor group that reviews these, but I've done a lot of the light water reactor design reviews. And I would say one way is that when somebody wants to qualify a material, that they could do that as part of their pre-submittal discussions, or maybe have some type of a topical report where they that they're qualifying material to use in their design, that they could submit to the NRC. But for a particular application on a particular design, I would suggest trying to get and is Raj still on this call?
I think he
must not be. Because
yes, I am.
Oh, he is. Okay.
Okay.
Yep.
So as far as getting regulatory approval, that would be somehow some interactions with the folks who review the advanced reactor designs would be helpful. But I understand that you conduct these tests and they're kind of new, And, then you do all this work, and then the regulator may say, well, why didn't you do this or why didn't you do that? I think the early interaction with the NRC would be very helpful.
Okay, yeah,
So
Yeah.
thank you.
was
Yeah,
this as
we've
part of
had
a particular,
yeah.
was
Oh.
the original question about the interactions with the regulator, was that associated with materials for a specific design that you were talking about?
No, actually, it came from Cheng, and it was really more associated with if we're doing so if we're doing microscale, small scale testing of materials under irradiation, will the NRC accept that data? And so should we be setting up either an ASTM standard for these very small scale techniques, or actually Kevin just added, should we do a round robin studies on these different techniques so that we can look at the uncertainties and verify the data? So that was
Well, I
where it
think
came
that
from.
when it gets to that point, and Raj, you correct me if you want to add, if you have a different outlook on this, but you could contact Raj, because of course the Office of Research would be involved in that, and then he could contact the folks who are actually would be the ones to review and approve these new materials, and then they could be involved maybe early on also. Raj, what do you think?
Yeah, well, I mean, we've had some interactions on the ion radiation aspect for a while, but Bob is right. What we want is we've had seen some kind of disparate efforts, here and there. It will be helpful if we see some coordinated push from the industry or DOE, or I think similar efforts are going on in OECD as well. So I think it's all over the map. I've talked to Dirk one time, and Isabella, who's also here, is can we actually have a plan, a solid plan for rapid qualification that we can comment on, and not from a regulatory point of view, but because we have research interactions, so we can engage. It does not mean endorsement or acceptance. That probably will help this. The licensees or vendors to provide additional information separately through the pre-submittal programs that Bob was mentioning. So it might be, we have a flexible approach. More importantly, it's something that we need to be engaged and understand. And Bob and his team, they have developed a pretty good guidelines for accepting or for reviewing AMT applications for AMT components. So we have done all we can. What we are looking for is we need to have some concerted effort in this rapid qualification that's more substantive and more focused than what I've seen in the last 3 years. 3 years ago, Kurt Tarani and we had organized a workshop in the same area. I have seen attempts all over the place, but we've not seen a solid plan and how we can. And in that probably could be a high level stage where the gaps can be filled in by individual licensees or their specific areas or designs.
Yeah, thank you for that point, Raj. And that's I could see both a concerted effort for rapid qualification to be part of this program for rapid qualification of materials for cladding applications. It also could be, and I think they've already stated it in their plans in AMMT as well, it might be slightly different for a structural material than it is for a cladding material. And so I could see us maybe working together on concerted efforts for rapid qualification in both those areas. So I really appreciate you making that point. And I don't know if I can keep up with all.
So it is important. So the fuels
Yeah.
is the cladding materials will actually be the first step towards fulfilling some of these structural materials requirements. So if you act, I mean, if you guys are coordinated, and you probably can lead the way, but the gaps can be filled in by other folks. What we're not seeing, at least I'm not seeing that. We are just hard pressed here to when somebody points to the NRC and say NRC is not accepting ion radiation data, why are you not endorsing it? I mean, those are nice questions to ask, but we really need to see much more in terms of a concrete plan, how that will pave the way for these kind of materials and manufacturing systems. So sorry,
No,
got
no, I
rid of
appreciate that. That's really important point, and I think that that's important both in the plan for this IMARC program as well as, and like I said, I've already seen it in AMMT also. So I've got a lot of I got a lot of comments here that I don't know that I have any
Could
that
I
are.
add one thing?
Yeah.
Can I just add one thing?
Yeah.
One thing to keep in mind is that I know research gets involved in a lot of things, but ultimately the Office of Nuclear Reactor Regulation makes the decision. Right? Research supports NRR and their licensing efforts, and so you have to remember that when you deal with the NRC, the people at the end who are going to say, yes, this is going to be approved, the people in fuels are completely different from the other folks. So anything that has to do with fuels or fuel cladding, for example, I'm a materials engineer, been at the NRC for 20 years, work on piping and vessels and everything else, but I know absolutely nothing about cladding. And I couldn't tell you any of the requirements, or I couldn't tell you any of that. So you have to make sure that ultimately in the end, you have the right, if you're talking to the people at the NRC, if you're dealing with fuels, you're talking, you have to make sure that the fuels people are involved. And if it's not fuels, if it's something that's pressure boundary or structural, then that would be a different group of folks. And you always
Yeah.
want to have the people who are going to actually approve it involved way up front also.
Yeah, thank you for that point. And I think, I mean, that's why I was saying that I think we want a rapid, qualification plan for cladding material. There also will be a, qualification plan for structural material. There may be some overlap, but they may not be exactly the same. They probably won't be. So that clearly is important point to make. And so does anybody want to make a direct comment as opposed to, there's a lot of, and I appreciate all the comments in the chat. There a lot of them have to do with ways of doing the round robin tests. Actually, Arun had a nice point about the fact that irradiation creep experiments using pressurized tubes have been done at HIFER and many other reactors and are planned in the future. So that's an important smaller scale technique. That's an in situ technique. It has a lot of data from previous irradiations, and it's nice to point out we can do that in HIFER also. Any other thing? Well, I mean, Jason Schultes, you had a comment about, I appreciate the ASTM E691 guidance for round robin studies, but you also had pointed out, are there any thoughts about mesoscale mechanical testing compared to microscale? And, I think it really depends on if you're doing it on a radiated material, it depends on, first of all, the radiation that you're doing, whether it's ion or neutron, but also it also I guess depends a little bit on the material you're trying to test. So if you're trying to test a large grain size 316L stainless steel, microscale is going to be difficult because you're always going to be just single grain or single crystal testing in a sense. Whereas if you can do it and cut it mesoscale, then you can maybe cover at least 10 grains across the thickness. And that's where I was pointing out. That's there is some work at at Los Alamos as well as at UC Berkeley, where they're developing femtosecond laser techniques for cutting out sort of 100 to 200 micron wide sort of specimens that would take forever on a fib. Those might be really nice techniques to continue and do direct comparison to either large scale or even micro scale testing. So yes, there is work looking at that, and I think that would be important to these studies also. So it's about 12:40. I don't know, Teresa, do you want, is all this captured? I mean, I think if we can capture all this, most of these are just good comments, and I'm not sure I need to go through each one, but.
I have captured everything into a Word document, so I'll forward that information to you.
Okay, so I think these comments are really useful. I'm not going to go through every single one, but let me just ask before I move on to the last slide, if there is a specific question or comment somebody wants to make and turn on their mic, we can do that. Otherwise, we're close to wrapping up here. So. Okay. So then I just went out of. So let me get back. Yeah. So I'm actually down to the last slide. First, I want to thank everybody for your input. I think I was really hesitant about doing a discussion by webinar, but I would really appreciate everybody through the chat and through discussions for stepping up and putting their input in. This has been really helpful, and I think it's going to help us lead to some strong priority research directions for this hopefully new program to start next year. So our path forward now is taking the input from this discussion here, as well as the talks, which we've got some really nice talks, some industry and some national labs, and using that to help develop priority research directions for this program, which would hopefully start next year. But I don't know. I wanted to also just thank Teresa and Holly, and actually Lori's not on, but I want to, Lori wasn't able to make it today, but I wanted to thank all the help that we had, and Eric as well, I guess, for pulling together this webinar that's been really useful. And I wanted to give Sue, if you're still here, did you want to say anything as we wrap up, or? Is Sue not?
I echo your thanks, and I will echo Mark's comment, thanking you for the great presentations, kind of giving it an overview on what our issues are and where we need to go and how we're trying to get there. All very useful, and thank you all for your comments. And like Stu said, if things occur to you, while you're at your barbecue on Monday, grab your phone, and hopefully you can still write coherent sentences and send us your thoughts, and that would be very useful. And even if you have ideas that end up not being right for this program, like you've seen throughout this workshop, we work very closely with the other programs within NE. We have several folks from AMMT. We had the Advanced Reactor program. We have the fuels folks on this call, and we work with them quite closely. So even if something really doesn't end up fitting with us, perhaps it'll be good input for another area. So don't hesitate to restrain yourself. Send us any comments that you have.
Okay.
Thank you, Stu.
Yep. Thank you. Thank you, everyone. Thanks for the comments. We'll be pulling this all together. And yes, The recording will also be available on the GAIN website. So you can not only find the slides, but you can also find the recording if you want to listen to me for 3 hours. No, actually, I didn't talk for the whole 3 hours. But
We'll try to have those up in the next couple of weeks. With the short week next week, we may not get them up until the following.
okay, well then I think
Yeah,
I will.
we have one hand up there.
Oh, okay. Yeah, Robert.
Yeah, I just wanted to add something. I was thinking about it here. You know, one thing we've heard about, you know, qualification materials for advanced reactors is that people don't understand the, you know, the obstacles that they're going to face with the regulator. But any pressure retaining, I say fuels is different, but anything that's for a structural pressure retaining application that's going to fall under Division 5, you know, of the ASME code, all of those things should start at ASME code. I guess before I was saying you should come and, you know, it's nice to come and tell the NRC what you're doing, but those things should go through the ASME code. Now, ASME code really doesn't address degradation, right? So they don't address the irradiated portion or the damage due to exposure to radiation. They don't cover that in code. So that would be something that you know, would be very, very important to discuss with the NRC. But any new material that you're going to qualify, you know, all the other aspects of it, you're definitely going to need to engage ASME code, which the NRC sits on. So the NRC is certainly aware of everything that's going on and votes on these things at ASME code. So I before we were talking about coming to the NRC, but I want to make sure I point out that, you know, it's not just coming to the NRC with some rapid qualification program for something that's pressure retaining. That really needs to go through the boiler and pressure vessel code first. But there are aspects that will be very limiting for that material, like radiation, that ASME code do not cover that.
I believe that's only for metals. For graphite, still it does.
Yes. Okay. I'm sorry. Yes, that you're right. And once you move into graphite, that's out of my area. I guess I'm talking about metallic materials, but anything that can go through code, that the code addresses, should go through code ideally before it comes to the NRC.
Okay. Yeah, and that's an important point. Thank you, Robert. And that's actually one of the reasons why on the AMMT program, they are covering ASME code case on many of the new materials, and also trying to find ways to advance that qualification faster. But like I said, there will still be some connection, I think, between that qualification and qualification for a cladding. So they're definitely ripe for a strong collaboration among the different programs. So
this is Sam
Sam's
Sham.
got his hand. Yep.
Yeah, I just want to echo Bob Davis' point. I think that yes, Division 5 is on construction, but in terms of some of those materials degradation mechanisms, I think that is very important to understand that, and also that in terms of ASME Section 11, Division 2, they start to sort of look at the operational phase that in terms of some of those reliability and integrity management program, they're all dealing with material degradation. So I think that that will also be sort of an organization that would be quite helpful in terms of getting all of this research into codes and standards, not for construction, but for operation. And that will so go hand in hand with the NRC licensing as well. Thank you.
Okay. Yes. Thank you, Sam. Any other quick comments before we close out? And then I think we'll if you have other things, you can send them by email to us. So, but all right. Well, then I will thank everyone once again. And if you have anything else, please don't hesitate to email me or Sue or Teresa as well. So, but thank you. All right. And I'll
Thank
stop
you.